So now this section on diagnosis focuses on results, or the second question, what are the results when we're critiquing a article? So let's start with a relevant question. So we have a 22-year-old female with a right ankle sprain. Her swelling is extreme, and you'd like to know how to diagnose ankle fractures, which can occur with these conditions. So our PICO is, the P would be athletes with lateral ankle sprains, the I would be swelling or other tests like the auto ankle rules that can diagnose a fracture, and then the gold standard or the comparison would be a CT scan or a radiograph, and the outcome would be sensitivity and specificity. So remember, the foreground problem here is that about 11% of all ankle fractures will have some type, or ankle sprain will have some type of fracture, some in the ankle, some in the foot. And so clinically, we want to know whether we need to get an x-ray or we don't need to get an x-ray to manage our patients correctly. So this discussion focuses in on what are the results and how can we interpret the findings from various studies. So we start with the definitions of sensitivity and specificity. And essentially what we're going to do is, with results for an accuracy study on a diagnostic test, we create a 2x2 table that looks something like this. So if we focus here, we put the reference standard results in the columns. So the true positives would be represented in this column, and then the true negatives would be represented in this column. And then we further subdivided all of the true positives by which ones the diagnostic test actually determined. So this would be the true positives. So the diagnostic test said it was positive and the reference standard said it was positive. And then which ones the diagnostic test said was negative, but in fact it was positive. So the false negatives would be here. So in this first column, we have all the positive tests on the reference standard, including the true positives and the false negatives. And then similarly, in the second column, we have the agreement between the reference standard and the diagnostic test. So when the diagnostic test was negative, this second row and this second column, those are where the true negatives lie. So, and then the mistakes represented by where the diagnostic test said it was positive, but in fact it was negative, are represented in this first row of the second column here. So once we have established a chart like this, it's easy for us to look at the numbers and see, okay, if there's a lot of true positives, that's good, that means it's accurate. If there's a lot of true negatives, that's good, it means it's accurate for a negative test. Then we also get a sense of where the false positives are and how many of those are occurring, and then how many false negatives are occurring. All right, and so essentially we can use this chart to kind of think about how we calculate sensitivity and specificity. So we can see sensitivity here, and the equation is we have the amount of correct answers over the amount of correct plus the amount of mistakes, the false negatives. So this single column ratio, and that's sensitivity. Now notice that basically what makes sensitivity high is if false negatives are low. And so in order to understand how to apply sensitivity well and specificity well, you want to focus on the mistakes that are being made, not the correct answers. And if you do that, you'll get it right every time. And you'll notice that basically if the false negatives are low, in other words, the amount of negative test results are going to be more accurate, you're going to think, okay, well, that means a high sensitivity means that it rules out the condition. And that's pretty much accurate. So what you can memorize, if sensitivity is high, then the condition rules it out well. So you can abbreviate that with SNOUT. So SNOUT. So if the test is negative and sensitivity is high, it rules it out. And in parallel to that, we have the second row, specificity, which defines specificity. And here the equation reads, it's the same thing, the number of correct answers, the true negatives over the true negatives. And in the denominator, we have the sum of the true negatives and false negatives. So if false negatives are low, then specificity is going to be high. And what we can see here is that essentially that if we focus on the mistakes again, so false positives go down, that means the value of a positive test is better. So if specificity is high and the test is positive, then it's going to rule it in really well. And that means that there's going to be few false positives. So that's how you interpret sensitivity and specificity. And here's those rules written out for you, which you can read on the handout. Okay, so let's apply these concepts to a ridiculously simple example where we take swelling measurements around the ankle after an ankle sprain, and we can see this distance here in millimeters, and we try to use that to estimate who needs to have a radiograph for a fracture and who we can just ignore the potential for a fracture because their swelling's too low. And so the next slides will have data both on people with swelling, our index test of interest, and then CT scans or radiographs, which represent our reference test of interest. Okay, so let's look here again at different ways we can create cutoff values for determining a diagnosis. And in this case, we're applying it to ankle fractures. What we can see here is, let's assume that we have some measure of swelling that's continuous. So now rather than a rule, we have a measure that we're measuring swelling, and we have a tape measure. We measure it around the ankle, and we have values that vary from 5 millimeters of swelling to 21 millimeters of swelling. And so if we look at this, we can see all these different swelling values, and then we basically split the values. We put all the fractures over here, and then we put all the non-fractures over here. And we can see that swelling does have a relationship to fracture status. So there's more swelling here, higher values, and there's less on the non-fracture side. But we also notice that it's not really exactly clear where we would draw a line to say, okay, people, above 14 or above 19, where would we draw the line to determine when to order a radiograph? So what this walks us through is different approaches to that. So in this approach that we're seeing demonstrated here, the cutoff values being drawn between 14 and 15 millimeters, which essentially plays the false negatives and false positives against each other. There's an equal number of false positives here as false negatives. So let's walk through that. So basically, if I say that the 14 millimeters and above, I'm going to send those people for an x-ray, what I'm really saying is everybody above 14 has a fracture, and everybody below 14 or below does not have a fracture. And in fact, I'd be wrong twice. I'd say, oh no, you don't have one, but that's not true. 2 people do, so those are the false negatives. And so similarly here, I would say all these people 15 and above have a fracture, but in fact 2 people do not, and so those people would be false positives. So this is an example of a cutoff value that minimizes both the false negatives and false positives. So this is that same data plotted in a 2x2 chart to determine sensitivity and specificity. So if you go back and count the values, we'd see 10. Here's our CT scan results with the fractures and then the no fractures. And then we have the test results where, below 15 millimeters and then equal to or above says they have a fracture. So here we have our results. Our 10 accurate results are true positives, our 12 true negatives, and then our false positives here, and then our false negatives here, and their resulting sensitivity specificity values. Now, let's suppose we wanted to define the test differently. Rather than optimizing the number of false negatives and false positives, we want to minimize any false negatives. We don't want any to allow anybody to not get an x-ray who might have a fracture. And so essentially what we would have to do is draw the cutoff at a different point. And so in this example, we want false negatives. We want to drive that to 0. And so where we would draw the line now is at 11 millimeters. And so by doing that, what we're going to do here is we're going to have many more false positives. So now we have 5 false positives and no false negatives. So let's look at how our 2x2 table looks when we do that. So here's our new cutoff values for the swelling test, and we can see what those are. And we're saying, in fact, all these people do have a fracture and all these people do not. Well, turns out we're right 100% of the time in terms of telling people they don't have one. We'll look at what happened to the sensitivity values. Our sensitivity values now are 100% are perfect. But what happened to specificity, so ruling in the disease? Essentially, it went down considerably. We have 5 false positives out of 17 that we said had it. So we sent 5 people for an x-ray that they didn't need. Essentially, though, this is a good example of a screening test where we're more concerned about not making a false negative mistake than we are about a false positive mistake. So we essentially don't want to exercise people in therapy that have a fracture because they need to be immobilized, not exercised. And so this is a good example of a screening test where we use a test that has low accuracy in terms of false negative or false positives. We use it to eliminate false negatives and then send them for another test to have the diagnosis confirmed. So let's look at the characteristics of a confirmation test. So a confirmation test is just the opposite of a screening test. For the screening test, we wanted to minimize false negatives. Well, in a confirmation test, we want to minimize false positives. A good example of when you might want to do this clinically is when you're performing a surgery on somebody or some invasive procedure where you're going to actually cause harm to the person when you do after you make the diagnosis. You'd want to be sure. And so essentially here in our example related to ankle sprains, we could draw the line where we said, okay, we don't want any false positives, so we'll put the cutoff value for ankle fractures at 18 or above. And by doing that, we would have all of these values then would be false negatives. So there'd be 1, 2, 3, 4, 5 again. Okay, and then we would drive false positives to 0. So let's look at what happens in our 2x2 table if we do that. So if we do that, here's our cutoff values for the positive tests in the top row and the negative tests in the bottom row. And what we can see is that false positives, which is this upper right box, is 0, and we can see that specificity is now 100% or perfect. And then we can also see here that sensitivity has gotten much lower, or there's a lot more false negative mistakes associated with that. So this is an example of a confirmation test where we minimize the number of false positives. However, the consequence is that we have more false negatives. So one way we can evaluate this in clinical tests is using something called the receiver operator curve, or a ROC curve. And that's what we see plotted here. So let's pay attention first to the x and then the y-axis. And on the x-axis, what we see is what's being plotted is 100 minus specificity. So essentially, what this is the percent of false positives that are occurring at different values of the test. And so on the y-axis, what we see being plotted is just the actual sensitivity itself. And so basically 0 errors on the y-axis will be 100%, and that means there'll be no false negatives. And then 0 errors on the x-axis will be 0, meaning that the false positive rate is 0. And so perfect score, a perfect test that has no false negatives or no false positives will have a score in this upper left-hand corner here. So it's interesting, right? And then the other characteristic of the ROC curve, which is nice, is that if we draw a diagonal line from the 0, 0 point to the upper right corner, that's if you flipped a coin and decided who had a diagnosis or not, this is the percentage of time you'd be correct. And so what we can know is if we use different cutoff values, so in our case we used an 18 millimeter cutoff, a 12 millimeter cutoff, and then right here would be the representation of the 14 millimeter cutoff. We could see that this the line that gets drawn on all the different cutoffs we use for swelling and determining ankle fractures is we get a curve that pushes up into this upper left corner. So what we're going to be able to do is use this to graphically understand how well a test is performing in making a diagnosis. And the more it pushes into this left corner, or the smaller this area becomes that's in blue here, then the fewer mistakes are being made. And the bigger the red area, the more correct decisions we're making using the test clinically. And so it gives us a graphical way of comparing two different tests that have different cutoff values, and then also to think about what cutoff value is best to use. So let's apply this ROC curve to an actual test that we would use clinically. So this is a study that was done by Diane Risley to look at the 5-time sit-to-stand task and its ability to identify or categorize people at falls risk who were community-dwelling ambulators anywhere from in their 50s to 80 years old. And we can see they used a stopwatch and timed the 5-time sit-to-stand task and then plotted ROC curves for different values of fallers versus non-fallers. And they essentially determined falling by following people for 6 months and noting who fell and who did not. So we can see first is that here's our ROC curve. So we have 1 minus specificity on the X and sensitivity on the Y. And the line for chance agreement here is drawn in the middle. And basically the red component is the amount that the tests would improve our decision making, and then the blue is the amount of mistakes we made. So if we include all subjects, the test is not very impressive. It doesn't really help our decision making very much. And if we look at the top row here of sensitivity and specificity in our table, we can see that the sensitivity and specificity are quite low, 66 and 67%, indicating there's a lot of false negatives in the case of sensitivity occurring, and then specificity in the false positives. But then if we subdivide the groups, though, we can see that the 5-time sit-to-stand, it changes, the ROC curve suggests it changes quite a bit for people under 60 years old. In fact, there's very few mistakes being made for people under 60 years old compared to people that are over 60. So a cutoff of 13 seconds would be about this point right here where the cursor is. So if we were to use a 5-time sit-to-stand task in patients or participants that were under 60 years old, our sensitivity and specificity would be quite high in the 80 to 90 range, or approaching 90, indicating many fewer false negative and false positive categorizations of people at falls risk. Okay, so now we've reviewed sensitivity, specificity, and a receiver operator curve, our ROC curve, in helping us compare diagnostic tests. But we also would like to look at something called the likelihood ratio, which people have introduced because it mimics the value of these clinical tests in our decision-making process. So let's back up a little bit and think about how our decision process works when we're making a diagnosis. Essentially, we start by facing off with the person and we have no preconceptions of what their pretest probability of having a disease is. And then we learn a little bit about them, and then we establish something called the pretest probability of the disease. Then we apply diagnostic tests, and what we're looking for is collecting negative or positive tests that either increase the probability that they have the disease to a point where it goes beyond an action threshold. We have to do a treatment, send them for a confirmation test, or actually think of them as being in the category of having a specific disease. So let's what we're really looking for clinically is tests or measures that put us beyond this action threshold, or confirm that they're not going to be at that threshold to make a decision. So let's start with, what is a pretest probability? Well, so essentially, if we are facing off with somebody with an ankle sprain, before we do any tests, we know that some people have fractures that have ankle sprains. So whatever that prevalence of having a fracture after a lateral ankle sprain is, that's the pretest probability. So before we apply a test, we already know to some degree what their chances of having the disease is. And so that's called the pretest probability. And what we're looking for is for the test itself to do better than the pretest probability and actually improve our decision making, or improve the likelihood that they either do or don't fall in that category of having a fracture after we apply the test. If it doesn't help us or doesn't improve the pretest probability in the first place, well, we really don't need to perform the test. So what we can see here is a value of something called likelihood ratios. So we can combine likelihood ratios with pretest probabilities to get an idea of how the combination of taking prevalence data and the results of a test should influence our clinical decision making. And so we are going to calculate both a positive likelihood ratio and a negative likelihood ratio. So this is the likelihood ratio has to do with the likelihood that the person has the category or the disease given a negative test, and a positive likelihood ratio is the likelihood they have the disease given a positive test. So one's about them not having the disease, the negative likelihood ratio, and one's about them having the disease, the positive likelihood ratio. And we can see here that sensitivity and specificity, this is the formula here, are used to calculate likelihood ratios, and their numerator and denominator change slightly, whether it's a positive likelihood ratio or a negative likelihood ratio. And in general, a likelihood ratio of 1 suggests that the test itself has no influence or shouldn't have any influence on our decision making. Or in other words, the pretest probability is just as good as doing the test, so we don't really need to perform the test. And negative likelihood ratios we want to be less than 1, and the closer to 0 they are, the better. And positive likelihood ratios, we want them to be much greater than 1, and we'll give some grading of different values, but if they're in the 5 to 10 range, they're considered pretty good.